For the function square root of 100 plus x, find a Taylor series expansion at the center a equals 0. If the center is 0, that's actually Maclaurin. This is Maclaurin series. You see, I skip the a after m, but they have both. MAC or MC, Maclaurin. I like skipping, less writing. Both are correct. So we want to find the expansion, Maclaurin series, because a is 0. That's a center. So you will see they will say Taylor series about a equals 0, around a equals 0, at a equals 0. That's the idea. So we are going to do the table method, so the formula. Let me write down for you the formula again. What if you skipped, what if you did not watch my previous YouTube video? And you should like and subscribe. So f of x, if it's differentiable continuous, which is actually differentiable, has this formula. It can be written as the sum c sub n coefficients and then x minus center to the n. N is from 0 to infinity. So in the office hours, I've seen a very good technique done by a student, writing it down again and again every time you do any homework. So at some point you memorize it. It's just really good. It's a really smart idea. Where c sub n's are found like so. N's derivative, plug in the center, divide by the n factorial. So every time, that's a formula. Every time the student saw a new example, he was writing this. And like the more you write, the more you remember. That just makes sense. I just realized it's a very nice suggestion to give in class. Kind of very good idea. He always, every example, he will write down the formula first. That's how you memorize it. If you write it down 22 times, for sure you'll memorize it for the exam. The first one is just original function at a plus the first derivative at a divided by 1 factorial x minus a plus the second derivative at a divided by 2 factorial x minus a squared. And let's keep going. This is what we put in the rainbow box last time. It's the same for all the functions. And now, what will be the difference? The derivatives, the point will be different. So I will put in yellow part, what's the difference? For each different function, derivatives, so these are coefficients. In yellow are coefficients. This will be different for every different functions because coefficients depend on derivative at the point. And the difference will be with the center, A is different for any different example. Everything else is the same. It will be square, cube, blah, blah, blah. 1 factorial, 2 factorial will be also the same. So let's do it. So I wrote it down, right, for our new example. F of x, f is a square root of 100 plus x. I just need now to find all these coefficients. It's a bit tedious work, so let's do it together so you wake up. My way is to write down the formula, but you don't have to. If you can put it right away into here, sure, just do that. I like organizing things into tables, but that's just personal preferences. So this is the first one. I have the original function. I will find the first derivative. I will find the second derivative. I will find the third derivative, and so on. They told me to find in your homework 3 derivatives is fine. So it depends on the problem. On a test, we'll give you usually 4 non-zero terms. So usually it's 4 derivatives, unless there's some zeros, you do more. So derivative of this, 1/2 goes down, 100 plus x to the minus 1/2. Does that make sense? Times 1. Don't forget chain rule, but it doesn't change anything here. So times 1. Derivative of the function inside. Next. 1/2 and minus 1/2 goes down, so it will be minus 1. I would say quarter. To see the pattern, you can do 2 squared, because now it will be 2 cubed, 2 to the 4, and so on. 100 plus x, that's just too short. Minus 1/2 and minus 1 is? Minus 3/2, thank you. Minus 3/2 go down, becomes plus, so it will be 3 over 2 cubed. 100 plus x minus 3/2 and minus 2 over 2 is minus 5 over 2. And you can see the pattern now. So next one, you can kind of calculate 2. It will be 3 times 5 over 2 to the 4, 100 plus x minus 7 over 2, and so on. Also, the sign is keep changing. Plus, minus, plus, minus. It's an alternating series. Do you agree with this? Derivatives, not too fast, not too bad, because it's derivatives, it's kind of, I don't want to stop on this too long. But this was your exam 2 in calculus 1 class when we did derivatives. Chain. Step 1, you find derivatives. Let me do steps. Step 1, you find derivatives. Steps. If you don't like the table idea, make it as steps. Also good. Sometimes derivatives takes too much space, so they don't fit into the table. Step 2, let me put it in circle. Step 2, plug the center. Plug your center. Center. In this case, center is 0, but it's not always the case, right? So plug the center A. A. What is the A for our case? No, actually, we change it to blue. Plug the center A, whatever A is. In our case, in black, it is 0. Original, so we need original function, we need first derivative, we need second derivative, we need third derivative. Original function at 0 is just, so f at 0, f prime at 0, f prime prime at 0, f prime 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 at 0, prime 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 prime. Now, at 0 it is square root of 100, which is 10. Nice, it's nice to have nice numbers. What is the prime, f prime at 0? What do you think? 1 over 20, I heard someone say it, good job. Let's see why. It is going to be 1/2, and then it's going to be 100 to the minus 1/2. You know, the good news is nobody requires you to simplify this. Not in the homework and not in the exam. So you will have trigonometric functions there, sine or cosine of pi over 4. Just keep it as it is. If you don't remember it, that is square root over 2 over 2. Keep it as it is. So I will keep it if you're hesitating, but 1 over square root of 100 is 1 over 10. 1 over 10 and 1 over 2 is 1 over 20. But again, you can just type it as it is. Charles, do you have questions?
I was going to ask, I thought you said it was going to be 20, so I was confused, but then you said 4 over 20, so I wasn't confused. Okay.
Nice. Good job. Next one, let me speed up. Minus 1 over 2 squared, which is 4. And then there is like 1 over 100. That's how I see it. Raised with 3/2. That's how I see it. Then you can calculate it. But again, you don't have to. That is not as important as the whole idea behind this. And the last one is blah, 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 repeat the whole thing, and I'm getting 3 over 8, 1, 2, 1, 2, 3, 1, 2, 1, 2, 3 zeros. 80, no, it's 800,000, 800,000. Plug it in. See, if it doesn't fit into the table, make it as a list of steps. Step 2, plug the center. Does it make sense? We're plugging our center into derivatives. Step 3, check this out. Step 3, we're going to divide by the corresponding factorial. So 1 over n, oh, we need the first one. 1 over n factorial, starting from 0. The first one we're dividing by 0 factorial, which is 1. The second one we're dividing by 1 factorial, which is 1. So I remember it's the same. So let's not write down it like this. What I'm going to do instead, I will have this. 10 divided by 0 factorial is the same as 10, and the other one is also stays the same. I just memorized that the first and the second stays the same, and the third one is divided by 2, and the fourth one divided by 6. Let's see why. So I will have 1 over 20 divided by 1 factorial. That's 1 over 20. Then I have minus 1 over 4,000 divided by 2 factorial. But 2 factorial is 2. So now it's going to be minus 1 over 8,000. Let me know if my handwriting is not good. 3 over 8, 1, 1, 1. 5 zeros. Divided by 3 factorials. 3 factorials is 6 because it's 1 times 2 times 3. So that will be, it will simplify with 3. So it's actually multiplied by 2 in the denominator. So it's going to be 16 and 5 zeros. 1, 2, 3. You guys put a dot sometimes. We don't do it in Europe, so I don't like it. Because in my country, this is decimals, only reserved for decimals. And Americans put a dot to show the 3 digits. So I don't do that. But you can do it if you want.
We put commas.
Yeah, commas. You guys put commas.
I think it's like Spanish countries.
I think so. Yeah, in my country, that's for sure decimal. So that's why, like, no, big no-no for us. That's what I was taking points off for doing that, so I'm not gonna be doing it, okay? My Mrs. Marple from grade 5th grade, she still traumatized me for taking points for that. That was a joke. So, now the 4th step, we're ready to use these coefficients. Those are my C/Ns. C sub 0, C sub 1, C sub 2, C sub 3. Maybe let me write it down. C sub 0, C sub 1, C sub 2, C sub 3. In one homework problem, they ask you to start with C sub 1, which is super stupid. I don't know why. So they just skip the first one without explaining the reasoning behind it. Just pay attention. The numbering should stay the same. So now you can see. The last step, if you have place, put it. If not, do it this way. Write it down. That everything will be multiplied by x minus center to the nth power. So the first one is not multiplied by anything because it's x minus a to the 0. But I can write it down for you. It will be multiplied by, so let me make like a table like so. It will be multiplied by x minus 0 to the 0. So that's just 1. The second one is multiplied by x minus 0. 0 is a center, right? To 1. Then x minus 0 to 2. Then x minus 0 to 3. Factorial and the power should match. So if it was 1, that will be 1. 2 factorial squared. 3 factorial cubed. That's how you know you did not mess up. Whatever is in blue, and I'll make it yellow. These are coefficients. So if they just ask you to write down coefficients, which is very popular in computer science, they just ask for coefficients. You just give them that as a list. But if they ask you to write down terms, then you add up while multiplying by corresponding ends. Kind of looks tilted. I don't like it. Oh, better. Now it has like a nice looking table. Like so. So the first row is original. That's why I'm separating it. But you don't have to. Others are derivatives. Now we're going to build this table. Look what I just did. Yellow are my coefficients. We found that they are in yellow. 10, 1 over 20, minus 1 over 8,000, and so on. Then it's multiplied by x to the 0, so I skip it. X minus a to the 1, x minus a to the 2, blah, blah, blah. So we're going to have fat thus, therefore, blah, blah, blah. Here's a Taylor series. In this case, actually, it's Maclaurin, but whatever. A square root, the square root of 100 plus x equals sign. This equal sign took lots of effort and a theorem to prove that actually it's not approximation. It's actually equal sign. That will be the original function at 0. That is 10. Let me color code it in blue. 10 is coefficient. The first derivative, so let me say that out loud. The first derivative at the center divided by 1 factorial. I'm looking to my table. It is plus 1 over 20. That is the first derivative, which gave me 1 over 20, divided by 1 factorial. But now it's multiplied by x minus 0 to the 1. That's just x, right? Should I write down? Maybe once, let me write down. X minus 0 to 1. So you see the whole nice shape of it. Now, it's a second derivative. Second derivative at the center divided by 2 factorial. I see it in the row number 3 because this is C sub 3. No, C sub 0, C sub 1 we did, C sub 2. C sub 2. In blue, it will be minus 1 over 8,000. And then in green, it multiplied by x minus 0 squared. Usually people don't put plus and minus, they put minus. So in blue are my coefficients. If we ask you just for coefficients, you give those separate as a list. Let's do one more because they asked for 4. It will be plus 4th, so third derivative at 0, divided by 3 factorial, and we simplified that. It's 1 over 16, 0, 0, 0, 0, 0. You don't have to simplify it. You can actually keep it as 3 factorial. Just put exclamation mark. Put parentheses nicely, and the computer will accept that. Multiplied by x minus 0 cubed plus, and keep going, keep going, keep going, keep going. This is an infinite series. While you are writing, I'm rewriting it looking nicely. Equals 10 plus 1 over 20x minus 1 over 8,000x squared plus 1 over 16, 1, 2, 3 x cubed. That is a nice looking answer. This square root 100 plus x equals this, and it's infinitely going. This is the answer. This is a Taylor series at 0, which is Maclaurin series, for the given function. What do you think about that? So first of all, that's the first answer. Second, I was like, why? Why are we doing all of this? Last time I tried to show you the applications, and then this time I will continue explaining it. The applications are pretty awesome because instead of working with this function or something even worse, like lots of upper level applications have horrible functions. What if you're working with something like, don't have to write this down, sine squared of x divided by arctan x cubed over ln x, everything is inside, e to the x squared minus 5 is a negative. So you want to find how fast this wind is changing the direction. What if you want to predict if this wind will cause or create a tornado in Texas, right? I should ask my friends in Texas if they're okay. Actually, there was something recently there. So that will be hard. To find a derivative means to answer the question, how fast? In Calculus 3, we're going to teach you vector fields, and those exactly will be the winds, how do they change as a flow, and so on. Electromagnetic fields. So the fields, we're going to teach you that. That is hard. It's easier to find derivative of this. I can find it like right now. It's 0 plus 1 over 20 minus 2 over 8,000x. Boom, I did it. Find derivative. So which one do you prefer? That's the whole point. If you can find approximation by the Taylor series, I would rather work with the right-hand side because right-hand side are just simple, stupid polynomials. It's very easy to differentiate them, integrate them, plug numbers. Like if I want to plug into this x 0.0018, that will take me lots of effort. But 0.0018 is better for the polynomials. We found polynomial expansion for the kind of complicated function. Square root of 100 plus x is not trivial. So instead of working with that function, we can work with approximation. And they tell us use, so it's a question B. So the question A was to find the Taylor. We did it. This is my Taylor approximation. Taylor series at x equals 0. Boom, we did it. Very good. Now they say B, use T sub 3, which is a Taylor polynomial of power 3, parentheses, x to the cube, whatever has to the third power. So that's, in some books, they call it P3. I usually like calling it T3 because it's Taylor, but they call it P3 because it's polynomial. So to approximate f at 1. So, or to find maximum, how do you find maximum? First, second derivative test. To find minimum, is it concave up? Is it concave down? Where's the point of inflection? I don't want to deal with a square root. I would rather deal with a nice polynomial cube function. It's over there. So this cut that we're going to call T sub 3 Now is equal, that's an equal sign. 10 plus 1 over 20x minus 1 over 8,000x squared plus 1 over 61, it's 1 million, right? 1,600,000 x cubed. That's called a Taylor polynomial, third power, because it ends up at t cubed. So we claim we found this polynomial because the f of x, that is a square root 100 plus x, is approximately t3. That is the idea. We know it's not an exact anymore because we cut it. It's a cut. We kind of kicked out the tail of it. And the tail gives more exact approximation. But we decided it's good enough for whatever project we're doing. Sometimes 25,000 terms is not enough. Sometimes 10 is enough. So the best computers in the world, some of them are located in America, in Los Alamos lab, and in New York. NASA, of course, owns the best ones. They can have millions of terms for you to be very precise, but then it will take lots of time. So cancer research, they need lots of precise calculations. But NASA space research does not need plus minus couple kilometers. Who cares? You know, just shoot there, maybe it should probably hit the huge asteroid somewhere. So that's exactly what happened recently. And I will tell you the story about it next week, because our own PhD student was working with math major PhD in applied math on the project, Earth Defense Project, shooting the asteroid using this. So it's like very applied. And I'll show you next week about her. We have an article in BBC News about her now. Using t sub 3. So they want us to find what is f at 1. Of course, you can like just say f of 1 is obviously square root of 101. Like, duh. That's the kind of obvious weird idea here. But we chose easy function because it's easy to work with it. So what is square root of 101? There's two ways to find it. Use some cool technology. So say computer, right? Computer is synonym of cool technology. Computer. Or use your own approximation of t sub 3. Your own, because you calculated. We just did it in front of you, like together. So computer will give you a better answer. If you check Wolfram Alpha or your graphing calculator, it gives you a very good answer. And we're gonna use that as like exact answer. Of course, it's still not exact, but it's a good one. It can give you like 100 decimals. While we're just gonna calculate as a human beings what we can. We're gonna plug 1 into t sub 3. It's in front of me in the box. The third power Taylor polynomial. It will be 10 plus 1 over 20 times 1 minus 1 over 8,000 times 1 squared plus 1 over 16, 1, 2, 1, 2, 3 times 1 cube. That is approximately 10. Obviously, it's 10 plus small numbers because as you can see, next number getting smaller and smaller and smaller. So it's 10 plus some decimals. 0, 4, 8, no, it's in front of me. 0, 4, 9, 8, 7, 5, 6, 2, 5. How did I find this number? I used not a cool computer, which is a calculator. Maybe I did table division and I figured out something like what is 1 over 8,000 and I actually calculated that using long division. Or maybe I use a calculator or Wolfram Alpha. Still, Wolfram Alpha is not as good as a NASA computer. So that's what we call approximate. Approximate answer. While the previous one we will call exact answer, even though it will not be exact. So step 3, so B, we found it. C, they ask you about the error. Find the error. That is what we teach specifically for STEM majors like engineers and physics major. I did not do that as a mathematician. Error is absolute value between exact and approximate. We don't care about the sign. We care how far we are from the good answer. So it's going to be error equals, let me give you the formula. It's always more or less the same. It's absolute value because we don't care about the sign. We want to know how far we are from the good answer. Exact, or the good answer, minus approximate, which is our answer. So we're going to have error, sometimes, usually it's E, equals absolute value of the square root of 101, whatever we have from the computer, minus 10, 0, 4, 9, 8, 7, 5, 6, 2, 5. And this is approximately 3.87911 times 10 to the minus 9. This is the error. So this is the bad stuff. The bad stuff, which means we're not exact. When we cannot exactly integrate, differentiate, or calculate things, we do approximation. You have this approximation, and then you get together with your team and says, shall we use this answer because this is what my error is. If you work with microbiology, depends on the situation, you can say, yeah, it's pretty small. How do you know? You put in computer. If error is less than 0.000001, it's good. In another case, 0.001. In another case, 0.1. So depends on what you're working on. This is pretty small, so you say, okay, the error is good. Let's keep the answer I found. And the answer I found was this one. If the error is too big, you have to choose another method to find the better answer, better approximation. Or do you know what you should do if the answer is not good? Yes. That's actually a very good question to ask people. What if this error is too big? Like 0.7, that's a big error in most sciences. 0.7, that's more than half. You just step, if you're working with surgery, so appendicite surgery nowadays is done by a robot. 0.7 centimeters is like, whoa, instead of appendicite, I actually just cut off some like very important organ. So that's why in microscience, it's actually pretty important. What do you need to do to improve the error? Yes?
Do you add more terms?
Yes. That was what you're saying? Yeah? Let's add more terms. We're not going to do that. But you tell, if people told you, no, mathematician or engineer or physicist, computer science, usually computer scientists do this work too. That's a bad error. As a doctor in medicine, I cannot put my patients in danger. Go home and recalculate whatever you was doing there. So what you're going to do when you go home, you add more terms, and then you add more, and then maybe up until like 100. Bring that, so you plug 1 again, right? With all those new coefficients in front of it. Bring that new number and new error, which now will be much smaller, and then see what they're going to say. Well, it's a team usually. Sometimes you decide, sometimes people who are in the field decide. So then they approve it, they put it in the robot. Now robot does appendicite surgery using these results. That's how lots of things were created, using mathematical modeling. Yes? Yes. Questions, ideas, suggestions? Have you heard about any of this? Do you want to add? That was very nice.